And yeah, we'll get into all this stuff. Obviously, we only have a couple of days left in the semester before finals week. So that means we probably won't get through all of these sections. That means a couple of these sections, like the chapter 10 stuff, will be optional. If you want to try those homeworks, that's fine. If not, that's all right too. You can, do those. If I don't cover something, then it won't be on the final. And we'll talk more about the final on Thursday, okay? So that's it. All right. So we had just dealt with systems of equations, systems of linear equations, and we saw what happens with two equations and two variables, a couple of different ways to solve those. All right, the elimination method, the substitution method. We can do some word problems, some mixture problems, some percentage problems. I'll show you how to set those up, and then we'll learn a new way how to solve those a little bit later. So I'll leave the solving for them till a little bit later. So here's the classic, what some people call mixture problems, what some people call percentage problems. Let's say we have two acid mixtures. They're going to be added together. One consists of 14% acid, and the other consists of 45. All right. How much of each should we add to make 210 milliliters of a 22% acid mixture? Okay. When you see it, or when you come across a problem like this turns into a system of linear equations in the following way. We're going to have a total, what I call a total equation, and then we'll have a percentage equation. All right. So the total equation is going to be talking about the total amount in the mixture. So for that, we need some variables. We have to have a 14% acid. We'll call the amount of 14% acid A for this problem. And we'll call the B the amount of the 45% acid. And obviously we want to mix those to get 210 milliliters of a 22% acid mixture. So that's the basic premise of this. So here are the two equations. The first equation is the total. I need to add A and B together to make 210 milliliters. So that's the total equation. A plus B is equal to 210. Okay with that. And then the percentage equation. Since 14% of A is going to be acid, the amount of acid is going to be 14% of whatever amount that is. Since B is 45% acid, the amount of acid that you're going to be adding from B is 0.45 of whatever the B amount is. And then the mixture, when you add those two together, so add them together, you get 22% of the 210 value. Okay. Now, I'm using the letters A and B You can use whatever letters you like. You can use X and Y. But if you're doing this on the Moodle or any program, and it tells you to use A for one amount and B for the next, use those letters. And then we have a system of linear equations. This is two equations, two variables, so we can solve it. We can solve it through substitution if you'd like. You can solve it through elimination if you'd like. Right now, what I'm going to do, just to save a little bit of time, is I'm going to solve through graphing, and I'm going to replace the A with the X and the B with the Y, so that when I graph it on Desmos, graph the system of linear equations on Desmos, I can do it efficiently. Makes sense? So that's what we're going to do. Just solve this. We saw how to graph with our calculator last time. If I'm graphing my Desmos, X plus Y equals 210 is my first equation. Second equation is 0.14x plus 0.45y is equal to 0.22 times 210. By the way, if you'd rather multiply that out, 0.22 times 210 is 46.2. So if you'd rather write 46.2 there, you can do that as well. Now, obviously, I don't see any lines in this view, because if you notice, like, you have to plug in like X of 210, Y of 0. So I got to scroll out pretty far to see these lines. But once we do see those, we can see that they do cross at a certain point. And that point is 155.81. 54.19. That means we need to add about 155.81 milliliters of the 14% solution with about 54.19 of the 45% solution. Okay. So that's what we're doing. Is that okay? So we create a total equation. We can create a percentage equation, and then you can solve it in whatever way you want it. Again, I solve using graphing on Desmos. You can solve by elimination. You can solve by substitution. Probably next class period, we'll see another technique of solving using what's called Gaussian elimination. Right? So. Now, we can do this with lots of other scenarios. We can do this with candy mixtures instead of acid mixtures. We can do this with monetary amounts instead of acid amounts. Lots of other scenarios. Let's do this one with monetary amounts because the language in this is just slightly different. Instead of giving a percentage at the end, it gives the raw number at the end. All right. So this says an investor puts $12,600 into stocks, doesn't know which stocks are going to bring more money at the end of the year, so he puts it into two stocks. Stock A earns 5.6%, and stock B earns 7.1% during that year. Then it says the investor made a total of $776.10. So A, I'll write as the amount they put into stock A. B, I'll write as the amount that this person put into stock B. And then they made 776.10 total. The question is, how much did they put to each stock initially? Once again, we're going to have a percentage equation and a total equation. Since the initial investment was $12,600, that means for the total equation, the amount put into A plus the amount put into B has to add up to $12,600. Now the percentage equation, if you recall, A made 5.6%. B made 7.1%. So this percentage equation is basically going to be an equation for how much was earned, or how much was made. So on the investment, however much I put into A, this person is going to earn 5.6% of A. They're also going to earn 7.1% of B, however much was invested into B. And at the end, instead of stating like, well, we made 6.7% of the original, instead of saying something like that, it just says we made $776.10 total. So instead of this being a multiplication on the right-hand side, it's just how much they made in total. All right. All right. We'll figure out how much they put into each. Again, I'll just solve this using graphing, make it very straightforward, hopefully. I got to use X and Y if I graph it on Desmos instead of A and B. So I'll use X and A interchangeably and Y and B interchangeably. And then again, Desmos is nice because we can zoom pretty quickly out and then back in. Notice that, where's this point of intersection? This point of intersection is at 7,900, 4,700. That means the investor put 7,900 into stock A and 4,700 into stock B. Does that make sense where we're getting at? Yeah. That's just solving by graphing there. Now, the last thing I want to cover, so that's how these word problem, mixture problems go. And obviously, I'm going to give you a problem to do, and it's going to say, well, what's the total equation? What's the percentage equation? And then obviously get the answers. Okay. We'll see other ways to get your answers. You may say, well, wait a second, use Desmos both times. Again, we'll show some quick versions of getting our answers next class period. All right. With some other matrices tools. Okay. Excuse me. But before we do that, before we get into some matrices, I want to lastly talk, and this will be really brief, about how to deal with 3 variables and 3 equations. We've been dealing with 2 variables and 2 equations so far. Now we want to deal with 3 variables and 3 equations. Well, if we have 3 variables and 3 equations, what we're going to do essentially is pare that down to 2 variables and 2 equations. So what we do is we pick 2 pairs of equations and we eliminate the same variable in each pair. So maybe we eliminate x's in each pair, or we eliminate the y's in each pair, or we eliminate the z's in each pair, if it's x, y, z variables. If I do that for 2 equations and 2 variables, then what that will have accomplished is gotten me down to 2 equations with 2 variables. Does that make sense? So if I go 3 equations, 3 variables to start with, eliminate 1 variable twice, now I have 2 equations with only 2 variables left, and then I solve it in whatever way I want to do that. So in other words, the goal is to go from 3 variables, 3 equations, down to 2 variables, 2 equations, and that's a realm I know how to deal with. So let's take a look at this example. Let's say we want to solve this system of 3 equations with 3 variables. X minus 2y plus z equals 6. X plus 4y minus z equals 10. And 2x minus 6y plus 2z is equal to 6. So I have to first decide which variable I want to eliminate. And when I do that, then I'm going to pick two pairs of equations to use. So I'll do what I'll call the natural thing. I will eliminate variable z. So I'm going to choose to eliminate z. And my first pair of equations are going to be equations 1 and 2. So equations 1 and 2 will be my first pair. My second pair, I'm going to use 2 and 3. Now, if somebody else wanted to do 1 and 3, that'd be okay as well. But I'm going to use 2 and 3. You see that? So I'll do 1 and 2 as my first pair, 2 and 3 as my second pair. So equation 1 and 2 are nice to eliminate z because they already have opposite coefficients on the z. I already have opposite coefficients. So if I want to add those two equations up, that will eliminate the z already. We'll have 2x plus 2y is equal to 16. Equation 2 and 3, equations 2 and 3 aren't quite as easy to deal with. If I want to eliminate the z, what I would do, we've done this before, elimination method. The 2 in front of the z I'll put in front of equation 1. Negative 1 in front of the z, I'll put a positive 1 there. And then I'll multiply through. We'll get 2x plus 8y minus 2z equals 20. And then this is 2x minus 6y plus 2z is equal to 6. Add those equations up. And I would get 4x plus 2y is equal to 26. So I picked two pairs. I eliminated the z in each pair. Now notice what I am left with. I'm left with two equations that only deal with x's and y's. And so I can move on and just solve this system, which says, I'll write that one first. 4x plus 2y equals 26. And then that second, 2x plus 2y equals 16. You could have written it either way, doesn't matter. You guys know what I'm going to do? I'll do another elimination step. This one, again, notice that if I just change the second equation, multiply it all the way through by -1. Then I do have opposite coefficients on my y. I see that? I could have multiplied -1 across every term on the first equation as well. Adding those up give you 2x is equal to 10. So x is equal to 5. Once we know x is equal to 5, we can plug it into one of those two equations. And I'll get y equals 3. Once I have both x and y, then I plug it into one of my original equations, like x minus 2y plus z equals 6. And that'll give me my z. Do you follow that? Doesn't matter which equation you pick on that original one. So again, I'm saying we have 4x plus 2y equals 26. So I plug in x equals 5, solve for y. Here we have that as one of our original three equations. I know x is 5. Now I know that y is equal to 3. That turns into a -1 plus z equals 6. Z is 7. All right. So the solution is when x is 5, y is 3, and z is 7. Some people would write that as an ordered triple instead of an ordered pair. They write an ordered triple. 5, 3, 7. When you write ordered triples, just like ordered pairs with other variables, you write it in alphabetical order. All right. So the x, y, z, alphabetical order. That makes sense. So there you go. That's how we solve a system of 3 linear equations with 3 variables. We take 2 pairs, we eliminate the z's on 2 pairs, which gives me 2 equations with 2 variables. All right. And then that gives me a 2 equation, 2 variable system that I can solve. And then I plug that number in, those numbers in to one of these 3. Doesn't matter, I picked the top one, but if you picked this third one, that would have been fine too. Is that all right? Now I will skip example 10. If you want to see how that's done, you can watch the video. It's the same deal. But if we were to eliminate the z, notice that one of those equations already doesn't have a z. So I can sort of use that equation as my first pair. if you will, right? And then I can eliminate the Z on the other pair and be good to go. Again, if you want to see the specifics of that, you can watch the video on your own. We're going to instead move right in to the matrices and matrix operations section of this class. All right, so we're going to deal with matrices in this class. And a matrix is just an array of numbers. So it's going to have some rows and columns. Usually we write square brackets around the whole thing. Sometimes people will write really big parentheses around the whole thing, but square brackets is the more used notation. You can see a few examples there. Okay. Now, we're going to talk about the dimensions of a matrix. This is how many rows and columns it's going to have. We say that we have an M by N matrix if the matrix has M rows and N columns. Like I said, these are called the dimensions of the matrix. They're also called the size of the matrix. So the size or the dimensions of a matrix are telling you how many rows and columns it has. So it's an array of numbers, the size of which is the number of rows and the number of columns. So if we look at our four examples that we have, this upper left-hand matrix on this slide has 3 rows and 2 columns. So it is 3 by 2. The upper right-hand matrix has 2 rows and 3 columns. So it is 2 by 3. We can see that 3 by 2 is not the same thing as 2 by 3. Obviously. So 3 by 2 on the upper left, 2 by 3 on the upper right. This bottom left matrix has 3 rows and also 3 columns. So it's 3 by 3. And the bottom right matrix has 1 row and 3 columns. So it is 1 by 3. That makes sense? So the layouts, the dimensions of each matrix, upper left, 3 by 2, upper right, 2 by 3, lower left, 3 by 3, lower right, 1 by 3. That lower left matrix had 3 rows and 3 columns. Whenever that happens, whenever the number of rows and columns meet, or I should say match up, we call that a square matrix. So a square matrix has the same number of rows as columns. Also, a matrix that I'll reference is the zero matrix. The zero matrix of any dimension is the matrix where every entry is 0. Just like the 0 vector. All the entries are 0, 0 matrix. All of the entries in the matrix are 0. And it can be any dimension that we want. So any dimension that we want, we can have a 0 matrix for that dimension. Notation-wise, we often use capital letters to denote a matrix. So matrix A usually is just capital letter A. And then the entries of that matrix are defined by what row and column they're in. So we say that the 1 entry is the entry in row 1 column. The 1, 2 entry is the entry in row 1 column 2. And we denote that with subscripts often. So we can see that if we're in row 1 column 3, that's the 1, 3 entry of the matrix. That's A1, comma 3. All right. And 3, 1, we are in row 3, column 1. All right. So that, again, is often the notation people use for matrices. To set up a matrix, we use a capital letter, and then the actual entries are denoted with subscripts. Okay. Now we're going to do a few algebraic operations with matrices. The first is we're going to add and subtract matrices. This is very straightforward. When we add or subtract matrices, we add or subtract them entry-wise. What entry-wise mean is if one element is in the 1, 1 entry of the first matrix, and we're adding a second matrix, then I'm going to add the 1, 1 entry to that with the 1 entry to the first matrix. Does that make sense? So the 1, 1 entries get added up, the 1, 2 entries get added up, the 2, 1 entries get added up, and so on and so forth. So, for instance, if we want to add these, 5 and 2 get added to 7. 7 and 0 get added to 7. 2 and -8 get added together and give me a -6. -1 and 1 get added together and give me a 0. And so on and so forth. -3 and 4 add together to give me 1. 6 and 4 add together to give me 10. And if we subtract, it's entry-wise as well. So 2 minus 6 is a -4. 3 minus 1 is a 2. -1 minus 1 is a -2. 7 minus -4, that's like a 7 plus a 4, gives me an 11. Is that right? This is pretty intuitive. If you were to guess how you'd add matrices of the same dimensions, that's hopefully what you would do. Just add the entries together. Now, here's the weird thing about adding matrices. What if they don't have the same dimensions? What if one of them is 3 by 2 and the other is 2 by 3? It turns out if we add and subtract matrices which don't have, or we try to add subtract matrices which don't have the same dimensions, we can't do it. So if you're asked to add two matrices with different dimensions, we should know that that does not exist. We can't do that. Right? All right. Good. Another operation on matrices that's pretty intuitive is scalar multiplication. Scalar is just a real number. So when we talk about a scalar, we're talking about a real number. And if I take a real number times a matrix, I just take that number and multiply it times every entry of the matrix. So 4 times the matrix 5, 7, 2, -1, -3, 6 gives me the matrix 20, 28, 8, -4, -12, 24. I take the same dimensions and I just take each entry and multiply it by 4. Or in the second one there, I multiplied by 8, just each entry multiplied by 8. So scalar multiplication and matrix addition, matrix subtraction, those are fairly intuitive processes. Hopefully that's how you would think you should add, subtract, and multiply a scalar times a matrix. I want you to try a couple of examples on your own. I'll write these on the board. Here we have 2 matrices added together, 2 matrices subtracted. I'll flip to another example in a moment where we take scalar multiplication and all that stuff. So try these on your own. All right, I'll go through this pretty quick. Since these have the same dimensions, we just add entry-wise. So we get 5, 1, 9, 17, -8, and 10 as the entries, obviously in this order. Okay, 5, 1 is in row 1, 9, 17 is in row 2, -8, 10 is in row 3. So we just add entry-wise, keep the same dimensions. When we subtract 1.8 minus a -6.3, that's like adding 6.3, we end up with 8.1 as the 1, entry. When we take 3.3 minus a -3.7, again, that's like adding 3.7, we're getting a 7 or a 7.0. -4.1 minus 6.1 is a -10.2. And then 2.8 minus 1.5 is a 1.3. Okay. And again, we're just entry-wise subtracting those. So adding and subtracting matrices of the same dimension works out nicely. It's entry-wise addition or entry-wise subtraction. Excuse me. Now let's look at these two examples. On that first example, what do we know that's going to happen? Yeah, it does not exist, right? Different dimensions. Therefore, that first example does not exist. Or I should say the solution does not exist for that. In the second example, this is just entry-wise multiplication. 6 times that matrix is 6 times every entry in the matrix. Six times 1.8 is 10.8. 6 times 3.3 is 19.8. 6 times -14.1. No, I'm sorry, -4.1. Excuse me. Is -24.6. And then 6 times 2.8 is 16.8. So when you do the multiplication, again, I'm going through it pretty quickly just because we're trying to do things low time in this class. We end up getting in the first row 10.8, 19.8, and in the second row -24.6, and then 16.8. Bear that. Now you can mix and match scalar multiplication and matrix addition. If you do something like 3 times -4, 6 12, 13 minus 2 times 3, 1, negative 1, 5. We're combining vector addition, I keep saying vector addition, matrix addition and scalar multiplication. Works just like vector addition, so that's why I keep saying that. So, in this, you multiply by the scalars first. When you multiply 3 times this first matrix, you get negative 12, 18, 36, 39. When you multiply the second matrix, you can either multiply it times a negative 2 or by a positive 2 and keep the minus sign out front. I'll multiply the whole thing by a negative 2 and turn the sign out front into a plus. Does that make sense? So I'll write it this way, plus negative 6, negative 2, positive 2, negative 10. Some people would do a minus 6, 2, negative 2, positive 10. That's fine as well. I like distributing the negative before I add, rather than subtract. When we combine these two matrices, they are of the same dimension, so we can add them. And this will give me a negative 18, 16, 38, 29. Is that right? Now, here's where things get unintuitive. Here's where things get not how you think they should be. We're going to multiply matrices. And you may think, well, the easy way to multiply matrices would be multiply them entry-wise. It turns out that that's not how we multiply matrices. When you multiply matrices, what you do is you take row M of the first matrix, called the lead matrix, and you multiply it times column N of the second matrix, the following matrix. And that is going to produce the AMN entry, I should say M comma N, but of the resulting product matrix. I'll go through this, we'll do this more next time, but I'll go through this in an example so you can see. Okay. Let's say we're going to multiply these two matrices. I have these on the slides, so it shouldn't be crazy. But I'll also write it down on the board as well. we're going to multiply -4, 6, 12, 13 by 3, 1, -1, 5. So the first thing I do is I focus on row 1 of that lead matrix, or the first matrix, and column 1 of the second matrix. Those two, I'm going to multiply. And when I multiply them, what we usually do is we usually think of taking this -4, 6, turning it upright, and multiplying it times 3, -1. So the -4 multiplies by the 3. The 6 multiplies times the -1. And then we add those two products together. Okay. That is going to give me the 1, 1 entry of the resulting product. Again, I usually think of this as sort of dynamic, where I take the row 1 and I turn it upright and I multiply it by column 1. So -4, 6, -4 gets multiplied times 3, 6 gets multiplied times -1, add them up. This is going to be -12 minus 6, which is a -18. Okay. And then I'll take this row, still row 1, and I'll go to the next column over. So -4, 6 is going to multiply times 1, 5. -4 times 1 plus 6 times 5. That's going to be -4 plus 30. And that's going to give me a 26. Now, I'm ending there because I've ran out of I've ran out of columns to multiply row 1 by. Everybody see that? So that's why I'm finishing the matrix now, because I'm finishing row 1 of the matrix because I ran out of columns to multiply by. Since I'm done with row 1, then I move on to row 2. Let me flip through this slide here. So I take row 1, column 1, then row 1, column 2. And now I'm done with columns in my tail matrix, my second matrix. So now I switch back to row 2 times column 1. 12 times 3 plus 13 times -1. When I multiply those. Again, I think of this as grabbing 12, 3, putting it upright. 12 gets multiplied by 3, 13 gets multiplied times a -1. And then lastly, we get 12 times 1 plus 13 times 5. Row 2 of the first matrix times column 2 of my second matrix. And that'll give me a 77. So once you get good at this, it goes pretty quick, but it does take a minute to get used to. 36 minus 30. 12 plus 65. So the product of those two matrices is this one. Okay. Does that make sense? All right. Well, like I said, today's class has got to end early. So this gives you some time to, if you want, work on homework and things like that. You actually have all the tools you need to finish 9-5. We're going to do some more examples of matrix multiplication, and we'll show some interesting features of matrix multiplication next time. And then we'll finish next time with other matrix stuff. All right. Gaussian elimination, and then maybe matrix inverses. Okay. All right. I will see you all on Thursday. Other than that, have a good